position Z, right? Okay? Then you can argue that I can predict the sound distribution. I can predict sound distribution on any Z, right? I know I gave you hard work last time, so he have been working all night, I guess, right? Okay, so that means using that technique, what I can do is, you measure the sound over here, look like okay, and then you can predict the sound at another plane, and that turns out to be like this. Okay? That is the fundamental concept of doing acoustic holography. Acoustic holography. This is a fundamental concept. Acoustic holography. Holo means entire. Graphy means graph. So acoustic holography claims that once you measure on the single plane information of the sound pressure distribution, then you can reconstruct the sound pressure distribution at any plane. That is fantastic. That is what described by using famous Mona Lisa picture. Okay? Now, let's move on to another topic. Okay.
이게 JKG 그걸로 이렇게 시프트시켜서 보는 것 같은데.
Z, we change the Z value. It's like a Z equal 1, Z equal 2, Z equal 3 meter, for example. Yes, yes. Yes. That is fantastic, right? That is fantastic. Reason is, recall this famous equation, Kirchhoff-Helmholtz integral equation. And if you choose dg, if you choose G to be 0 on S, then this go away, right? And if you choose G, free space Green's function, where R then I do have this, and I measure this on every R0. In this case, on this plane. Okay? Then I can predict any point using this equation, right? Right? If I measure, then this means I summing up the sound pressure at discrete point, say delta R0 and maybe I said I use index index n, and I measure from n equal 1 to n, and n equal 1 to n, right? Then I can reconstruct the sound using this Green's function, okay? And if I select R, if I change the R at various points, then I can always predict it, right? And note that this is the spatial information on this plane, and this is the Green's function. And then what I do is I take Fourier transform and take Fourier transform of this and then convolve it and produce sound pressure at any point, right? That is the basis of, again, similar expression of acoustic holography, similar the other way of explaining acoustic holography. Okay. Maybe you look at the text again to understand precisely what does it mean by that. Scattering and diffraction. Okay. Scattering and diffraction. Any question? No? Okay. What is a scattering? What is diffraction? Okay. Suppose there is a war and I generate the sound. Depending on the thickness of wall, the sound over here is different. Okay? Depending on sound, you can hear my voice, right? But you cannot see me. Okay? That is typical physical phenomena of diffraction. For the diffraction case, there is a zone where we cannot see the source that we call the shadow zone. But the diffraction depends on wavelengths as well as the size of the wall. Simply, suppose that you have a big wall and the car is passing by over there and you are hearing the sound over here. Okay? You cannot see the car, but you can hear the sound. Especially low frequency, because low frequency emit large wavelengths sound. And the scattering, for example. You have a sphere and you have some incoming wave. Then due to the presence of small sphere or cylinder, there will be some sound is scattered. Okay? All of them is induced by impedance mismatch in space. Generally speaking, impedance mismatch in space can generate a diffraction or scattering and so on.